Chase. Hi, Chase.
Hey, Rose, how you doing?
I'm doing fine. Sorry, time got away from me a little bit. So I'll be right with you in a second, okay?
All right.
Actually, I'm buttoning my shirt off screen.
Ah,
Be right there.
are we still going to be going over percentage yield today?
Okay, Chase, what can I do for you? Chase,
Yeah.
what can I do
Are
for
we
you?
still are we still going to be going over percentage yield today?
No, I hadn't planned on it.
Oh, are we moving on to something else?
Yes, we are.
Ugh.
Let's talk you through it, okay? And let's see. Okay, percent yield isn't that tough.
It's the thing is when it gets to the percentage yield, the concept isn't hard. It's the amount of it's when I get hit with a problem.
All right, let's walk
If
through it,
I knew how
okay?
to set the problem up and know what to look for, it'll be a lot easier. But it's I don't really understand how you can figure out the steps, like how you can put them in a specific order just knowingly.
Okay, we're gonna start this simple and then build up, okay?
Okay.
Plus. I don't want to do that. Let me. Plus CO2, CO3 taken. And we're going to do it simple. O2, let's see, O. All right, so we're going to need 2 of these. And that's balancing us, okay? All right. I got 34.5 grams of NH4 CO3. Okay. How much NH4 Cl do I make? Okay. All right, Chase. Hi, Victoria.
Hi.
Okay, Chase.
Yes, sir.
Remember, when we're doing stoichiometry, 3 steps. You wanted to have a step-by-step breakdown of this? Stoichiometry is always 3 steps. Turn your known into moles. Turn your moles of known into moles of unknown. Then get the grams of your unknown. Okay?
Okay.
Now, nitrogen is equal to 14. Okay. Hydrogen is 8 times 1. Carbon 1 times 12. And oxygen is 3 times 16. Okay. We're just going to make this easy. Okay. So if I add all this, the molar mass is equal to, okay, 48 and 12. This is 48 and 12 is 60, plus 8, 68. 68 and 28 is 96. Okay. Now, Chase, first step is to get moles of my known. How do I get moles of my known?
You take your molar mass and then you multiply it by the ratio, which would be
Nope.
2 over 1.
No,
No.
how do we get moles? We need moles first.
Oh, do you take your molar mass and then multiply that by 1 mole over
What are we starting with, Chase? What did I give you? I'm so magnanimous, I give you things in every problem. What did I give you in this problem?
molar mass?
I gave you that, but what else did I give you?
Oh, I see it. 34 grams of NH4.
That's where we're starting.
Okay.
Okay. So I want to change this into moles. So what's going to go on top?
Huh?
I'm changing 34 grams into moles. What's going to go on top? What do I want to end up with, Chase?
So you're going to want to put your 1 mole and then over the molar mass?
Okay. That seem reasonable to you, Chase?
Yeah. I was pretty confused for a second because I forgot you gave the 34 grams of NH4.
Okay, this gives me 0.35 moles of right? What do I want to know? What do I want to know? What did I ask you?
You want to know the I don't remember.
I want to know how many grams of ammonia chloride I'm going to make, right?
Yep.
So Chase, I got moles of ammonium chloride. Is there a relationship between moles of ammonium chloride and moles of ammonium carbonate?
Yes.
What is that?
The CO.
No. Okay. Remember how I told you to read a chemical equation? 1 mole of ammonium carbonate reacts with 1 mole of cobalt chloride, cobalt 2 chloride, to make 2 moles of ammonium chloride plus 1 mole of cobalt 2 carbonate. Okay, Chase?
Okay.
So what is the relationship between ammonium chloride and ammonium carbonate?
I don't really know what you mean by what the relationship is. Are you asking for like the ratio or?
Yeah, exactly.
Oh, 2 to 1.
2 to 1. That's exactly what I'm
Okay.
asking for. So
Okay.
I got 0.35 moles of NH4 carbonate. Now, if I want if I want moles of NH4Cl, what goes on top of what now?
2/1.
I'm not going to bother doing the labeling here, but it's 2 moles of NH4 over 1 mole of 2 moles of NH4Cl over 1 mole of NH4 twice CO3. So this, if I do that math out, I get 0.70. 0.70. I said 0.70. Okay.
Okay.
Now, what's the last thing? What's the last thing that I do?
You're gonna want to take your moles, and then you're gonna multiply it by, I don't know if you're multiplying it by the 34 grams or the given
No,
mole mass.
Okay, look when we're reading the problem. Okay, when we're reading the problem, the 34 grams is associated with the ammonium carbonate, right?
Correct.
Does nothing about ammonium chloride. The 96 is a molar mass of the ammonium carbonate. Says nothing about ammonium chloride. The only way I get to anything about ammonium chloride is when I do the molar ratio and I take the moles of my ammonium carbonate and multiply it by 2/1 to get moles of ammonium chloride.
Mhm.
Now, how do I go from moles of ammonium chloride to grams?
You're trying to get rid of moles.
Thank you, Victoria.
Do you multiply it by like 100 or something?
No.
What would it be? Because I know either the
All
molar
right,
mass.
all right, let's look. How do we go from grams to moles?
We found them.
Molecular weight.
Yeah.
And going from grams to moles, then we put 1 mole on top of grams.
Yes.
So if I'm going from moles to grams, don't I have to do the exact opposite of it?
Yeah.
So I'm going to be putting grams over 1 mole. I just got to figure out what my molecular weight of ammonium chloride is. And that's 35.5 plus 4 plus 14. I hate this calculator.
53.
53.5.
How did you get the?
How did I get the?
Oh, did you just find the atomic weight of NH4Cl?
Yeah, that's all. The
Okay.
molecular weight. That's all I did there. So I ended up with 37. Okay. 3-step process, Chase. And obviously you need to learn how to go from moles to grams and from grams to moles. That's the first thing you're going to have to do. When you're going from grams to moles, you're going to multiply it by 1 mole over the molecular weight. When you're going from moles to grams, you put the molecular weight over 1 mole. Okay? That's the first thing. First thing we need to do, we need to determine. Okay? Second thing, it's a 3-step process. Stoichiometry always is going to be a 3-step process. Turn grams of your known into moles of your known. We did that by taking 34 grams, multiplying it by 1 mole over the molecular weight, which was 96. That gave us 0.35 moles of ammonium carbonate. Second step, turn your moles of known into moles of unknown by using the molar ratio. Look at the balanced chemical equation. The molar ratio is going to be the coefficient of your unknown over the coefficient of your known. In this case, that's 2 to 1. So I took my 0.35 moles of ammonium carbonate and multiplied that by 2 over 1 to get 0.70 moles of ammonium chloride. Last step, turn the moles of my unknown into grams of the unknown by multiplying it by the molecular weight over 1 mole. I do that math out and I get 37 grams. Okay, Chase,
Chase,
you
I wrote
started
it out in
original.
chat.
What's
All
that?
right.
I wrote
Victoria?
out I wrote out how to get it, like the
Okay.
basic setup in chat too. So you have a way
Template.
to get it. Yeah.
Okay, now
Thank you.
Chase, your original question was percent yield. Okay? Now, the 37 grams, is that the amount we should theoretically get? If everything went exactly right and I mixed 34 grams of ammonium carbonate with excess cobalt chloride,
Yeah.
shouldn't I theoretically get 37 grams of ammonium chloride?
Yes.
All right, I do the experiment. I do the experiment and I get 34 grams. All right. I've actually gone ahead and put 34 grams of, we'll change the numbers. We'll go for 30. Okay. I've actually put 34 grams in with excess cobalt chloride. And I've done the experiment. I come up with 30 grams. Percent yield is equal to experimental divided by theoretical.
And then you multiply it by 100, right? Okay.
Mhm. Okay. In other words, what you got divided by what you should have got.
What you shoulda.
Okay. Times 100. Okay.
Okay.
Now, we got how many back? We did the experiment. How many grams did we get back?
7.
No.
30.
Case, where'd you come up with 7?
These questions you're asking are confusing.
Okay, you got to listen to me and you got to retain a little bit.
I am retaining. It's just like the wording.
All right. Now, I told you, we started with 34. We went through, we did the stoichiometry. So we theoretically should have 37 grams, correct?
Yeah.
All right. Now, I told you that we actually got 30 grams back.
Okay.
We did the experiment and only got 30 back. So what did we get back, Chase?
30.
What should we have gotten?
34.
Nope, 30. Let's look over this slide. What should we have gotten back?
Oh, 37.
37. So I'm going to take my 30, divide it by 37 times 100. And that's going to give me a percent yield of
81%.
81%.
Well, 81.08. So 81.1.
Well, sig fig wise, it's 81.
Yeah.
Okay. So basically, Chase, I knew you weren't having problems with percent yield because percent yield, it's fairly easy. All you got to do is identify what you got experimentally,
Yeah.
divide that by what you got stoichiometrically, and multiply by 100. Okay. So I knew that you were having problems with you're having problems with the stoichiometric. 3
Yeah.
steps. Turn your known grams into moles. And you do this by taking your grams and multiplying it by 1 mole divided by the molecular weight. Second step, turn your moles of known into moles of unknown by using the molar ratio. Where do you find the molar ratio? You look at your balanced chemical equation. The coefficient in front of your unknown goes over top the coefficient in front of your known.
Hello.
Hello, Omar. Third
How you doing?
step. Third step, we take our moles of unknown now. We want grams of it. So we multiply it by the molecular weight over 1 mole. Chase, each and every stoichiometric problem is going to go through these 3 steps. It may have some things put on them in addition, but each one of them will have these 3 steps.
Yeah, it's just going to be something I'm going to have to practice. And
As with anything,
yeah,
okay? I have all right. Okay. Somebody, I've been saying this all along. You guys are hopefully paying attention here. What have I said the first step is?
convert grams to moles.
Okay. I have,
I'm getting it.
all right, I'm looking at this though. I have 2 reactants. I have an amount of each reactant. What type of problem does that make this?
Limiting reagent.
Limiting reagent. So I got to find out how much silver the copper can make, and I got to find out how much silver the silver nitrate. Which one do I use? Do I use the larger or the smaller amount?
Don't you use both?
Nope.
The smaller.
Smaller amount.
Smaller amount, because the limiting reagent will be limited by the amount that it has. It can only produce so much. There will be an excess of the other reagent. So I got to take this. I got to take my 2 reagents. First step. All right, guys. I got 22 grams of copper. What's the first step?
Convert to moles.
Convert to moles. And who was taught? Jennifer. Thank you, Jennifer. I don't want you
Mhm.
speaking for the next 15 minutes.
Okay.
Okay, I do that. And I get,
Numbers. You got
okay. What's my molar ratio between copper and silver?
2 to 1.
What goes on top, Victoria?
Silver.
All right. I've got half of my problem done. I got 44 grams of AgNO3. What do I do? What's the first step to convert that one?
Do the same thing you did with the Cu, pretty much.
Okay, tell me. Tell me, Chase.
So you put it over 1 mole over the weight.
Atomic weight, molecular weight of silver is 143. Ooh, this turns out to be a fairly good problem. Now, what's the relationship between AgNO3 and silver?
Would it be 1 to 1?
Kind of. I'm going to call it 2 to 2.
Yeah, same thing.
So if I have 22 grams of copper, I can make 0.70 moles of silver. If I have 44 grams of silver nitrate, I can make 0.3 moles of silver. Which one do I use?
Use the AgNO3.
The silver nitrate. And the last thing I do is I multiply the 0.30 times 107, and this gives me 33 grams silver.
Where did you get the 107 from?
That's the weight of silver.
Oh,
The
okay.
atomic weight of silver. It's not exactly, it's 107 point something, but it's close enough for these purposes. Ladies and gentlemen, I'm offering it out there. I've been calling on specific people. What are you not understanding about this? Talk to me.
To be honest, sometimes the numbers just jumble up. Like when I'm writing it out, I always have to like go back and stuff. I don't know if it's just me, but like,
Hunter,
you know what I mean? You got to like be careful.
Hunter, that is why I keep on repeating ad nauseum. I keep on repeating out the 3 steps to do this. Turn the known into moles using 1 mole over the molecular weight. Turn the moles of your known into moles of unknown by taking the coefficient of your unknown, putting that over top your coefficient of your known. Then turn your moles of unknown into grams of unknown by taking the molecular weight of the unknown, dividing it by 1 mole. Yes, you're absolutely right. You can get all jumbled up and crazy.
Say that last part again. You said take the
moles,
unknown.
the moles of your unknown, multiply it by the molecular weight of your unknown divided by 1 mole.
So moles of unknown divided by molecular weight of unknown.
No, that's not what I said.
Say it again.
I said you take your moles of unknown, you multiply it by the molecular weight of your unknown divided by 1 mole.
Okay, and then divided by, okay. Thank you.
All right. Let's start off with an apology because I got out of class on Thursday and I was really pissed off at myself because I didn't do a good enough job explaining it to you. Really and truly, to go from one thing to the other within a chemical equation, to do stoichiometry, 3 steps, and I've explained what those 3 steps are. Slow yourself down. Take it 1 step at a time. Get through the 3rd step. You will have your answer. Now, the hardest problems you guys have to deal with are how much excess reagent do I have left? I have 2 amounts here, an amount of sodium and an amount of zinc oxide. Okay. Now, there's another way to do a limiting reagent problem. I can pick one of these 2. I could find out how much of the other reactant the first one needs. And based upon that, I can determine the limiting reagent. Does that make sense to you all? I have 34 grams of sodium, 70 grams of zinc oxide. I'm going to pick my sodium and find out how much zinc oxide I need. I turn my sodium, first step, turning sodium into moles by taking 1 mole and dividing it by the atomic weight of sodium. So I have 34 grams of sodium. That equates to 1.48 moles of sodium. Now, I'm going to turn that into how much zinc oxide I need. I have a molar ratio. What's my molar ratio, Hunter? Zinc oxide to sodium.
It's almost 1 to 2.
It's not almost, it is 1 to 2. Because there's a 2 coefficient in front of the sodium, a 1 in front of the zinc oxide. So that relationship, 1 mole of zinc oxide to 2 moles of sodium. So if I have my 1.48 moles of sodium and I multiply it by 1 mole of zinc oxide over 2 moles of sodium, this means if I have 34 grams of sodium, to react that completely, I need 0.739 moles of zinc oxide. Is what I'm saying right now making sense, guys? Shake your head, Victoria.
It is, and I don't want to be rude, but it's a little fast.
Okay, Hunter.
Because I want to do the math, I'm trying to follow along with the math as you're saying it, like doing it on my calculator.
Okay. Divide 34 grams by 22.99. What do you get, Hunter?
34.0. You said 42. Say that number.
34 divided by 22.99.
That's 1.47. We're doing 3.
1.47 something.
Yeah, 4.7 something, but we're doing 3 sig figs, right?
Yeah, I got it to be round up to 1.48 moles.
Okay.
All right, now the moles of sodium get multiplied by the molar ratio. There's 1 mole of zinc oxide for 2 moles of sodium. So I'm going to multiply my 1.48 by 1 over 2. In other words, I'm going to divide my 1.48 by 2, and that gives me 0.739.
I got 0.74. 1.48 divided by 2 is 0.74 on my calculator.
It's the rounding that's
Yeah.
killing you.
Yeah.
Okay. All right. So this is what I need of zinc oxide to react with my 34 grams of sodium. Now I got to ask myself a question. Do I have it? I have 70 grams of zinc oxide. So I'm going to find out how many moles of zinc oxide I have by multiplying it by 1 mole over the molecular weight of zinc oxide, which is 81.39. So I do that division out. I get that I have 0.860 moles of zinc oxide. I need 0.739. Do I have enough?
Yes, you have enough.
If I have enough, then the sodium is the limiting reagent. Does that make sense to everybody?
Yeah, now that makes sense.
Okay, so if my sodium is limiting, I got to figure out how much zinc oxide is left. Would you agree that I started off with 0.860 moles of zinc oxide?
Yes.
How much zinc oxide did the sodium consume?
Well, we just put that 0.74 into the zinc oxide. That's how much it used up.
So I started off with 0.860. I used up 0.740 or 0.739. All I got to do is subtract the two of them.
0.47.
No. 0.860 minus 0.739, Hunter, equals 0.121.
I'm sorry. I made a error on my calculator. You said 0.860 minus 0.39, right?
0.739.
Oh my Lanta. 0.481.
No.
My calculator's jacked up then. Hold on, let me get my other one.
Okay, guys, everybody. I started off with 0.860 moles of zinc oxide. I used up 0.739. If I subtract the two, that tells me how much zinc oxide is left. All I have to do then is multiply by my molecular weight of grams per 1 mole. This means I have 9.84 grams of zinc oxide left. Questions, guys? Hunter, you're rubbing your head.
I'm sorry, my ears suck. Yeah, no, you're completely right. I did it on my calculator and I looked at the screen and
That
You're right.
is, that makes me feel good, Hunter, that you tell me that I did my math correct.
it's me. I suck at math. So
Is everybody seeing how I came up with the amount of zinc oxide left? All right. Now, when I did this problem, I happened to get lucky. I happened to pick the limiting reagent as the one, that's the one I picked to figure out how much of the other reagent I needed. What happens if I don't pick the right one? I have a new problem here. Magnesium plus silver fluoride makes magnesium fluoride and silver. If I start off with 63.4 grams of magnesium and 655 grams of silver fluoride, I'm going to pick magnesium. Again, guys, first step. What is the first step? Any stoichiometric problem. Turn the grams into
moles. Turn the grams into moles.
Moles.
Okay, so I've got 63.4 grams of magnesium. I'm multiplying it by 1 mole over the atomic weight. This gives me 2.
The magnesium's atomic weight. How much is the magnesium atomic weight? I have my periodic table out. I'm just trying to look.
24.31.
31.
Okay, thank you.
So I divide the 63.4 by the 24.31. I start off with 2.61 moles of magnesium. But what's the relationship between silver fluoride and magnesium?
2 to 1.
2 to
I have a
1.
question though. Why did you pick magnesium? Because it's a smaller number, or does it matter which one you pick first?
Katie, That's as good a place as any to start. It's a crapshoot.
But the thing
Yeah.
is, for some reason I feel like when I pick the smaller weight with grams, it's usually that's the reagent.
It's a crapshoot, Andrew.
All
It
right.
really is. You're basically, Katie, picking a smaller number of grams is a good place to start. But you don't have to, as I'm going to illustrate in a second or two, all right? Now, Katie, I got my 2.61 moles of magnesium. What is the molar ratio between silver fluoride and magnesium?
2-to-1.
So how much silver fluoride, how many moles of silver fluoride am I going to need?
2?
No.
Oh, no,
Two?
1. Sorry.
No.
What
Katie,
do you mean? Of silver
I've
fluoride?
got 2.61 moles of magnesium.
Oh, 5.22.
So I've got to multiply my 2.61 by 2 moles of silver fluoride over 1 mole of magnesium. I need 5.22 moles of silver fluoride. That's what I need to react entirely, my entire 63.4 grams of magnesium. Now I got to figure out, do I have it? I got to take my grams of silver fluoride, turn that into moles by multiplying it by 1 mole over the molecular weight, which is 126.87. This gives me 5.16. If I have 63.4 grams of magnesium, I need 5.22 moles of silver fluoride. Do I have it?
No.
No, I don't. So silver fluoride is my limiting reagent. So now I kind of got to go backtrack to figure out how much of the magnesium the silver fluoride will use up. Okay, I have moles of silver fluoride. What is my molar relationship of magnesium to silver fluoride?
Someone said 2-to-1, right?
1-1.
Not right, guys. What's the coefficient in front of magnesium
1,
and silver fluoride?
2,
So if I'm going to convert my silver fluoride to magnesium, what number goes on top, the 1 or the 2?
2. No. 2.
What number is, we want magnesium. What number is in front of the magnesium?
1.
So I'm going to put 1 mole of magnesium over 2 moles of silver fluoride. So I started with 0.516 moles of silver fluoride. I'm going to multiply it by 1 mole of magnesium over 2 moles of silver fluoride. This means I used up 2.58 moles of magnesium. But I started with 2.61. If I started with 2.61, used up 2.58, don't I have 0.03 moles of magnesium left? If I have 0.03 moles of magnesium left, I then multiply that by 24.31 grams. This gives me 0.7 grams of magnesium left. Hunter, you looked at me with a bad gaze there. Where did I lose you?
I'm sorry. My grandma is here. She was asking me a question. It's not that I'm looking at you with a scold. I literally just put this like menthol. I have a thing on my face right here. So it's like.
Is this going to be too much information, Hunter?
No, it's not. No, it's not. I'm just.
No.
It makes me
Okay.
sweat.
No problem. You're getting where I'm going, where I went with this, right?
Yeah. No, I'm getting it.
All right, ladies and gentlemen, we have those of you that are in the face-to-face laboratories this week. We're going to have a workshop of stoichiometry and limiting reagent. Make sure you know how to do stoichiometry. Make sure you know how to do limiting reagent. Before I go on, questions?
Why would you multiply the 0.03 moles by the 2431 mole?
Is this Chase?
It is.
Okay, Chase. All right. Do you see if I have 0.516 moles of silver fluoride that I would end up using up 2.58 moles of magnesium?
Yes.
Because all I did was relate my silver fluoride to my molar ratio of magnesium over silver fluoride. Okay?
Okay.
Now, if you remember, when I started out, I had 63.4 grams of magnesium. When I converted that to moles, that meant I originally had 2.61 moles of magnesium. Got you with me, Chase?
Yep.
So when I did my stoichiometry, I found out I used up 2.58 moles of it. So to find out what's left, I took my 2.61, which was the original moles of magnesium I had. I subtracted the amount I used up. This left me with 0.03 moles of magnesium. To convert that to grams, I simply multiplied it by my atomic weight of magnesium over 1 mole. This gave me 0.7 grams of magnesium left.
Okay.
I have a question.
I'm here.
Can you go over how we were finding the ratios again? I know that we're looking at the coefficients.
That's all it is, Hunter.
So you just, if there's one element, that's just one. And if there's two, like zinc oxide, that's two.
No, you're looking at the actual coefficients in front of the chemicals in the balanced chemical equation.
Okay, if it's not, okay, obviously if it's not balanced, we're gonna have to balance it first. But
Exactly.
let's say there's no coefficients.
If there are no coefficients, then it's 1-to-1.
Even if it's like one element and then
If I give you this, I'll fix one little thing here. Okay, I give you that.
yeah.
When I'm reading this chemical equation, 1 mole of sodium hydroxide reacts with 1 mole of HCl to make 1 mole of water and 1 mole of NaOH.
Okay, I get that. That's fine.
So when you're looking at the molar ratios, you are literally looking at the coefficients in front of the individual compounds. All right. Okay,
That just
Hunter,
looks like a nightmare.
that is my balanced chemical equation.
Yep.
So can you tell me, Hunter, what the molar ratio is between barium phosphate and phosphoric acid?
Yeah.
What is the coefficient in front of the barium phosphate?
In front of the barium phosphate, it's 1, right?
Exactly. What's the coefficient in front of the phosphoric acid?
It's on the outside, it's 3,
No,
but on the inside, or it's just 1.
no, phosphoric acid.
Sorry.
What's the coefficient?
It's 2.
Yeah, the coefficients are the big numbers that go in front of the chemicals.
Sorry, I was looking at the barium on the right side.
Okay. When you're dealing with molar ratios, it's the ratio of the coefficient of one chemical over the coefficient of the other.
Yeah.
So in this case, it would be 1-to-2. What's
1
the
to 2.
ratio between water and barium hydroxide, Hunter?
Okay, the barium hydroxide, the water would be 1.
No. Hunter, what's the coefficient in front of water?
Well, it just says H2O.
No, it doesn't. What's the number in front
Oh,
of the H?
I'm looking at the top. Okay, on the bottom it's 6.
Okay. So what is the molar ratio between water and barium hydroxide?
Okay, so it would be 6 for water, and then the barium hydroxide, which is the 3BaOH2. So it'd be 6 to 3. So then it would be 2
That's
to
it. That's the answer.
Yeah.
Okay. The
Right.
molar ratio, all you do is take the coefficient of one of the compounds, put it over the coefficient of the other.
Okay. Yeah, I just didn't know which water you're talking about because there's one on the bottom, there's one on the top. You know what I mean?
Okay. All right. Now, I'm about 15 minutes behind right now. Okay. So we're going to have to work in. We need to work in solutions today. We need to get through solutions so that I can talk about acids, bases on Thursday. What we're going to do with solutions, I'm going to go through some terms because you kind of got to know what we're talking about first. We're going to go through mass percent. Mass percent is the same concept as it was before. We're going to deal with molarity. We're going to deal with calculations on solution preparation, dilution equations, and yes, we're going to deal with stoichiometry.
Yay.
So, a solution is nothing more than a homogeneous mixture of two substances. Generally speaking, when we're talking about solutions, we generally like to think of one of them being a liquid, although that is not always the case. Solutes and solvents can be a liquid, solid, or gas. What we breathe in is a solution. It's a solution of nitrogen, oxygen, and a whole bunch of other little gases that are there. Brass. Brass is a mixture of copper and zinc. We have a solution. It's an alloy. An alloy is nothing more than a solution of two solids. You mix copper and zinc, you have a solid-solid mixture. Now, the parts of a solution. A solute is what's being dissolved. A solvent is the thing doing the dissolving. Generally speaking, the solvent is usually the larger portion. So solute, what gets dissolved? Solvent, what's doing the dissolving? Aya, you out there? Guys, I'm having a whole bunch of you that are skipping out. You're logging in and then skipping out. Aya, are you there?
Yes.
Thank you, Aya. Aya, you put salt in your water to make pasta. What is the solute of your salt water?
Dissolve.
What is the solute?
Would it be like NaH2O?
No, this is simple. Let's go simpler than that, guys. Okay?
Isn't it just the salt?
The salt.
Just the salt, guys. The solute is what's being dissolved. You put salt in the water, doesn't the salt get dissolved? So if the salt is being dissolved, what is the solvent?
The
Water.
water.
The water. Okay? If you want to make napalm. You want to make napalm. You put styrofoam in gasoline. What's getting dissolved?
Styrofoam.
The styrofoam.
So that is the solvent or solute.
Solute.
Solute. The gas
What's
thing's
doing the
solvent.
dissolving?
The gas.
Gasoline.
Gasoline.
I thought
Oh.
you were legit gonna do a chemical formula for napalm. I'm like, please God, no.
That'd be sweet.
Do you notice it's always the guys that want the fire and want the explosives?
Yeah.
I don't want that crime to come across my desk. No, thank you.
Man, I can't wait to make that now. Just kidding.
No comment. Okay. We also have to realize that there's a degree with something that can be dissolved. Okay. A solution is considered saturated if no more solute can be dissolved. Has anybody ever watched a Popeye cartoon ever?
Yeah, a
Yes.
bunch of times.
Yes.
All right. What does Popeye say right before he beats the snot out of Brutus?
Why? You looking for a fight or something? I don't know. He says something
I
along those.
can't. He says, I can't take no more. That's what saturated is. The solvent can't takes no more.
I'm feeling very saturated with life right now.
Mhm. I'm sure, Hunter. So, if we have a saturated, we also have to have the other end of it, which is unsaturated. If you can put more solute in, then it is unsaturated. Now, how do you tell? You're
Hey, I have a question.
Go
if you-
ahead, Hunter.
If you put more solute in something that's already saturated, will that solute will it not dissolve?
No, it won't. Now, Hunter, I'll put it back to you. How can you tell if a solution is saturated?
Probably the formation of a solid. That's my-
Absolutely excellent. If you see solid in the solution, if there's solid at the bottom, your solution is saturated.
Also, if gases, like if you're doing something with liquids, then the formation of a gas could also indicate that, possibly.
No. Erase that thought, Hunter.
All right,
That is not a good thought.
Why is
Okay.
it not? Why is it not a good?
Why is that not a good thought? What did you just say?
Well, if you have like a liquid, right, and you put a bunch of solid into that liquid, and the solid dissolves into that liquid. Once it's saturated and it starts forming a gas, then could that be an indication that it's saturated?
No,
I think that's just going through a physical change.
it's going through a chemical change if you're going from something that is
Oh,
dissolved in
yeah.
water to a gas.
Oh, that's right. That's right.
So you're actually
solid-
involving it. That's why I'm telling you, forget
Yeah.
about that. You're actually
Okay.
involving a chemical reaction there, Hunter.
That makes sense. Sorry.
All right, so you have all this solid on the bottom. Is there any way you're going to be able to get that solid into solution? Can anybody think of a way you can get it in there?
Add energy to it, or
Exactly, Hunter. Heat it up.
yeah, heat it up.
If you heat it up, can't you get more of the solid to dissolve?
I guess it depends on the heat capacity of that solid.
Generally speaking, when you're heating it up, you're making the water more active. And so therefore it's going to get more of the solid dissolve. What else? What else can you do to that solid?
Stir.
Come on, guys. You guys have all made Kool-Aid. Your mothers have made you sit there and stir this Kool-Aid until you get it all dissolved, right? So if you agitate it, you can also get more dissolved. Mila, have you ever made rock candy?
Honestly, no.
Ah, it's a great thing to do with the kids. It's
I'll have to
absolutely
try it.
fantastic.
I'll
So
have to
what you do with rock candy, you dissolve sugar in water and you heat it up. Put more sugar in there, heat it up. And you also do this when you're making Mai Tais, but that's another issue. This is a simple syrup solution. You keep on putting sugar in there until you get there's so much sugar in the water that you can't put more in, and yet you're able to put a little more in because you have a perfect situation.
I'll have to do this and then drop him off with grandma. 'Cause this sounds like a crazy night after that.
Oh, it gets better because you put dye in there.
Oh,
You put
nice.
dye in there and you get different colors for the rock candy.
But
Nice.
isn't that how they used to make pot ash? Like in the early days, they would make potassium that way, right?
I'll trust you on that. I don't know. Could be. Could be. So we have this super saturated solution. It's got more sugar in there than it can hold. Then what happens is you disturb it by putting a piece of string in it. Then what happens is all the sugar clumps on it and you've made rock candy. Now, another thing that we talked about a little bit in lab a couple weeks back, and that is something called an electrolyte. An electrolyte is nothing more that when it dissolves in water will conduct electricity. The two requirements are that it needs to be ionic, because ionic substances are charged. They can help carry a charge through the solution. The other thing it needs to be is soluble. So an electrolyte needs to be ionic and it needs to be soluble. So what's actually happening when we're dissolving something? We have water. Water is known as a polar solvent. What that means is we have the white hydrogens here and we have the red oxygen. Well, the electrons are floating around, both the oxygen and the hydrogen, but they spend more time around the oxygen. So every time you see the red ball here, that means that the red ball has a negative charge on it. And the two white ones have a positive. So water actually has a negative end and a positive end. Now, what happens when we get sodium chloride? Well, all of the negative ends of the water, all the oxygen ends, surround the sodium and separate it away from the chlorine. Similarly, the waters with the positive ends surround all the chlorines, separating it from the sodium. So the waters literally erode the crystals away. And so the waters completely surround the ions, separating them from one another. And that's basically how electrolytes work. Now, here's a very important concept in chemistry, and that is like dissolves like. Does oil mix with vinegar?
No.
No.
That's because oil is non-polar. There are no charges around the entire oil molecule. Vinegar is polar. Like dissolves like. Unlike does not dissolve like. Oil and vinegar are, one's polar, one's non-polar. They don't dissolve each other. On the other hand, water will dissolve vinegar. They're both polar molecules. Like dissolves like. Polar solvents dissolve polar compounds and ionic compounds. Non-polar solvents dissolve only non-polar compounds. Okay, we've been basically talking about what solutions basically are, how they come about, but we need to talk about solutions in two terms. One is what makes up the solution, and the second thing, the concentration of that solution. And the concentration is the amount of the solutes in a given amount of solutions. And we're going to have a couple couple different parameters we're going to need to talk about to describe concentration terms. And those are mass percent and molarity. There are going to be others you're going to need to know in the future, but for right now, I just want you to know these two. Mass percent, thank God, it's no different than it was before. You're going to take the part, divide it by the whole, and multiply by 100%. You've got the mass percent. What is the mass percent of a solution made by mixing 33.9 grams of ammonium chloride in 100 grams of water? Victoria, ask your dog.
She doesn't know math. She's a dog.
You have
Okay,
30.
so we should find the part and the whole in this scenario.
Okay, what's the part?
The part looks like it's going to be 33.9 grams.
Okay, absolutely right. Now, what is the whole?
The whole is
100.
going to be the 100 grams of water.
Is that true?
Yeah.
Yes. No.
Who said no?
Jennifer.
Jennifer, why is it not the whole?
Because your mixture or your solution is both the NH4Cl and the water. So
Okay,
Does
so then what's
everybody
your
understand?
33.9?
1 second, Hunter. Does everybody understand what Jennifer
Oh.
just said?
Yeah.
The
Oh, that
whole
makes
is
sense.
going to be what's dissolved as well as what's doing the dissolving.
Okay.
So in effect, the whole is going to be the 33.9 plus the 100. So our mass percent of this solution is not 33.9%, but in fact, it is
130.
30. Go ahead.
Wait, you're adding them together?
Absolutely.
Oh, so it's 133.9.
Well, the mass percent is going to be 33.9
yeah.
divided by 133 point.
Okay, I'm understanding.
So
So
instead of having a
0.25.
So it's
Hunter, I'm sorry, I
20
didn't hear you.
it's 25.3%.
Correct. Hunter, you said something. I can't hear
Sorry,
you.
I'm sorry. My sibling was bothering me. I apologize.
So
No.
uncivil.
Yes. So 33.9 divided by 133.9, you get
That-
0.25 for me.
25.3%. Remember, you have to multiply it by 100. Okay? We have 44.7 grams of lead nitrate and 125 grams of water. Let's see. I want to grab somebody. Please don't answer it until I call somebody. Brian. Brian, you out there? Cash.
Yes.
Okay. Were you listening to what we were just doing, Cash?
Yeah.
All right. So you have 44.7 grams of lead nitrate and 125 grams of water. Tell me how to figure out what the mass percent is.
I don't know.
Okay. I don't know. It's a perfectly good answer. Aaron. Gate.
Yes.
Okay, Aaron.
I'm here.
Okay. Solve it together, guys. You have
Okay.
44.7 grams of lead nitrate. That is placed in 125 grams of water. What is my mass percent, or tell me how to solve for it?
Yeah.
What's my part? Wait, guys. Mass percents are nothing more than part divided by whole.
You gotta add.
Victoria,
Oh, sorry. Am I banned from talking for the rest of the
Per-
class?
Not for the
so
rest of the class, but
you add
yes.
you add 125 by the 44.7, and then you divide. I'm doing it right.
Nope, I think you're doing it a little wrong.
All right, never mind.
You've got, Gate, you've got the idea. You're adding the 44.7 and the 125. Now, is that the part or is that the whole, Gate?
That's the whole.
All right, now what's the part?
You divide it by 1.00.
No, Gate, let's look. We got 44.7 grams of lead nitrate and
I think I have the
125.
answer.
Gate, what's
Yeah.
the part? I want to know the mass percent of lead nitrate. What's the part?
Oh, damn, kind of confused on this one. Can I get a visual?
Wait, can you pass it to me?
Go ahead, Hunter.
Okay, so the part is going to be 44.7.
Gate. I asked the mass percent of lead nitrate. When you get asked something like that, it's going to be the mass of the lead nitrate. So,
Oh, okay.
okay, what do you divide the 44.7 by? You had it earlier, Gate.
I thought I had this one.
1.00.
No,
I'm so confused now.
remember, Gate, you're dividing part by whole. What's the whole weight?
So 125 plus 44.7. So it'd be
Exactly.
169 something.
Yes. So basically,
169.7.
Yeah.
you're dividing the part, which is the 44.7, by the whole
Okay,
weight,
by
which is 169.7.
And can I do the next step?
Go for it.
All right, then the next step, you would do 44.7 divided by 169.7, and then you times that by 100, which gave me 26.3.
Finest kind.
Oh shit! All right, Einstein. All right.
Finest kind. Okay, guys, I'm not going to get too much more in the mass percents because literally speaking, we did a whole day, a better part of 2 days dealing with this. All you got to remember about them, it works the same way in solutions as it did when we were dealing with masses. Okay? There's another term that we really need to get down. And that is molarity. Molarity is moles of solute divided by liters of solution. That's what molarity's definition is. Moles of solute divided by liters of solution. Now, does this look like something you've dealt with in the past? Victoria,
Yes.
you can answer.
The STP?
No.
No.
Does this equation look like something you've dealt with in the past?
Yes.
What?
So when we were doing stoichiometry, when we were doing all the conversions, that's what.
Not what I'm driving at.
It was the lesson right before stoichiometry.
Nope. Way back, way back. First test.
Density.
Density. Okay, remember, isn't density equal to grams over milliliters, right? We can use that same thing. It's just the same kind of relationship, only instead of calling it the density triangle, we're going to call this the molarity triangle. If I have moles and liters, there's a line between them. Moles divided by liters will give me my molarity. If I have my moles and my molarity, if I divide my moles by my molarity, I'm going to get my liters. If I have my molarity and my liters, since those are both on the same level, I multiply them. Molarity times liters will give me moles. If you don't like that, just pay attention to the labels. molarity. You're going to take moles divided by liters. If you want liters, now you're going to take your moles and you're going to divide it by your molarity, which is the same thing as saying moles divided by moles divided by liters, which is the same thing as saying moles times liters over moles. So in other words, when we divide by the molarity, we multiply by the reciprocal. When I do this final math problem out, moles cancels with moles, I'm left with liters. If I want moles, my molarity gets multiplied by my liters. And again, I have to realize with this that my molarity is moles per liter. So if I multiply it by liters, liters cancel, and that gives me moles. You're going to have to become facile about doing this. What is the molarity of a 100 milliliter solution containing 15.6 grams of sodium hydroxide? Okay, I look at this problem. I want molarity. Molarity is equal to moles per liter, correct, guys?
Yes.
Yeah.
Do I have liters, or do I have a way of getting liters?
You have to convert milliliters to liters first.
And by the way, guys, you're going to get tired of doing this. 100 milliliters is equal to 1 liter divided by 1,000 milliliters. In other words, every time you want to change milliliters into liters, you move the decimal place 3 places to the left. Okay, so I have 0.100 liters. All right. Do I have a way of getting moles?
Yes.
Yes.
How do I
Yes.
have it?
You have to take 15.6 grams times 1 mole over the molecular weight of NaOH.
Okay, 16, 23. Okay, it's 40. Okay, so first thing, I take my 15.6 and multiply it by 1 mole over 40 grams. That's equal to 0.390. Did I not warn you guys that you're going to be doing a lot of conversions from grams into moles and moles into grams? Keep that aware. That's what you should be working on right now. So I've got my moles of sodium hydroxide. It's in 100 milliliters or 0.1 liters. So I take my 0.390 divided by 0.1 liters. This gives me a solution of 3.90 molar. Questions, guys? Questions?
Can we get another visual?
Amazingly enough. All right. How many moles are contained in 250 milliliters of a 0.600 molar solution? Kaylin, put the kitty down.
Sorry.
What did I say? What did I say molar solutions were? What's the label for molar?
Moles?
Per?
Oh, moles per liter.
Okay, so can I convert this 0.600? And guys, you should do this. you really should change molar solutions, change the label immediately to moles per liter. It will help you. So Kaylin, can I get moles out of this if I know I have 250 milliliters of a 0.20 or 0.600 molar solution?
Yes.
How am I going to do it?
Are we gonna multiply it
By what?
by 0.25? Oh,
And by the way, if you didn't see how that was done, it was 250 milliliters times 1 liter divided by 1,000 milliliters to give you 0.250. So all I'm going to do is take the 0.250 and multiply it by 0.600. This gives me 0.150 moles. Guys, you now have your third tool. I just gave you your third tool on how to create moles. If you have the concentration in molarity and you know the volume of your solution, you can multiply the two of them together to get moles. Any questions on this? Does anybody need me to make up a new problem?
Professor, can you just go back to the previous slide, please?
This one, I'm sorry, this one?
Yes, please. Thank you. Just stay there for a second.
Want to see my dog? Smile. Can you even see her?
No.
So Professor,
Yes.
just a quick question. For that next slide that we just worked on, you're just basically moving the whole number to a decimal. You're just putting a decimal in front of it. Is that basically what it is?
Are we talking about the 250?
Yeah.
Okay. When you're changing milliliters into liters, you can go ahead and do the 1 liter over 1,000 milliliters and then divide the 250 by 1,000. Or you can just simply know that all you have to do is move it 3 decimals to the left. So 250 milliliters is automatically equal to 0.250 liters.
Right. And then all you did to get the answer was divide 0.600 by 0.250.
Did not divide. Remember,
Multiply.
multiply.
Yeah, that's what I meant.
600, that a molar solution is moles per liter. So all I have to do is multiply it by the liters to get moles.
Okay.
Rosina, are you good now? Rosina,
Yes, thank you.
are we good?
Yes, thank you.
I saw your dog, Professor. She kind of blended in, but I saw her. She's a good dog.
No, she's not. Okay.
I have 3 cats.
Preparing solutions. If we want to go from grams to molarity, okay, we have 25 grams of sodium chloride. That is dissolved in 250 milliliters. What is the molarity of my solution? Okay, simple enough. I want to know the molarity. In other words, I want to know my moles per liter. I have, stop. Thank you. Thank you. I have 25 grams of NaCl. It is in 250 milliliters. Let's do the easy one first. In order to get molarity, I need both moles and liters. Can you convert 250 milliliters to liters?
Yes.
How much is it?
That's by 1,000, right?
Divided by 1,000. So we have 0.250 liters. Now, I need moles. I have 25 grams and I have a molecular formula there. How am I going to get moles, guys?
Okay, take
got-
the 25 grams and you can times it by the molecular weight.
1
Is
mole
that
over the
true?
molecular weight.
1 mole over the molecular weight.
Yeah, that's what I meant. I mean, it's essentially the same.
No, it's not the same, Gunter. Okay. Now what do I have to do?
You
Oh yeah, I'm bugging.
times it by, I'm looking at the guide. I may be
Nope,
cheating a
don't.
bit. Okay.
Don't look at the guide, Victoria. Look up here. What did we say molarity was, Victoria?
Please hold. It's moles of solute over the liters of solution. So you
Okay.
take 0.427 over 0.250. I'm dropping everything.
No.
So you should get, how many sig figs do I need? 3. 1.71 moles per milliliter. No, yeah.
Moles per liter.
For moles per liter, sorry.
Okay.
I'm following you.
All right. Similar problem. How
Wait, can
many?
you go back to that last slide really quick, please?
By the way, this solution is not in the PowerPoint. Are we good, Mila? You're sitting there with your thumb in the air, Mila. Are you good?
I think she
Oh,
froze.
yeah, my thing froze. Yes, sir, I'm done.
All right.
Sorry. Thank you.
We have another problem. How many grams of sodium chloride would it be required to prepare 500 milliliters of a 2 molar solution? Okay. Do we know, can we figure out the molecular weight of sodium chloride?
Yes.
All right.
It's
Can
50.
we determine moles?
Yes.
So if we have moles and we have the molecular weight, can we get the grams we need?
Yes.
Okay, let me write some things down. All right, somebody other than Victoria. If I have 500 milliliters of a 2 molar solution, can you tell me how many moles I have from that? I'll rewrite it. Can somebody tell me how I get moles out of this?
You multiply the liters by the molarity.
Simple enough. 500 milliliters times 1 liter divided by 1,000 milliliters gives me 0.500 liters. I just multiply that by 2.00 moles per liter. And this gives me 1.00 mole. Okay. So I now have 1.00 moles of sodium chloride. I want to know how many grams. Come on, guys. How do you go from moles to grams?
Molecular weight.
Molecular weight. Who's answering these?
Me.
No, I know it's not you, Gaith.
I'm not allowed to anymore, but it's Mariah, that is.
Is Mariah? Is it
Yeah.
Mariah?
Yes.
Thank you. So I'm going to take my 1.00 moles, multiply it by 58.5 grams per mole to get 58.5 grams. We started off the problem. How many grams of sodium chloride would be required to prepare 500 milliliters of a 2 molar solution? What I have to realize when I'm looking at this problem, I've got a volume and I've got a concentration. I can get moles. I also have the molecular weight. So if I have the molecular weight and I have moles, I can multiply the two of them to get the grams. All right. Last question. What volume of water is required to prepare a 0.2 molar solution from 7.81 grams of sodium chloride? Okay. Now, if we look at this backwards and we look at our triangle, how do we get liters from molarity and moles?
Moles divided by molarity.
Exactly. Moles divided by molarity. I really wish. Damn.
Wait, you really wish what?
I really wish this thing wouldn't go all kind of crazy on me. Moles divided by molarity will get liters. Basically, was that Mariah yet? Was it Mariah or Rosina?
No, that was Rosina.
Rosina, okay. Rosina just used the molarity triangle and she realized that if I want liters, I divide moles by my molarity. Okay?
Wait, there's a triangle?
Yeah, I'm saying, what is the triangle? Is that between molarity, moles, and liters? Are you saying
Yes.
the relationship between
Yeah,
them?
there are two things on the bottom, one on the top. Think of this like a triangle, just like you did the density.
Oh, I was just setting it up as like an X problem.
Mariah, that works as well. Remember I said you could do this with labels as well. You came up with the right answer, right, Mariah?
Yeah.
Continue doing it that way. But if we're dealing with the triangle, moles, there's a line between moles and liters. Moles divided by liters equals molarity. There's a line between moles and molarity. Moles divided by molarity equals liters. Molarity and liters are on the same level, so molarity times liters gives me moles. That's how you deal with the triangle. All right, so if we would have the moles and the molarity, we would get liters. Right, guys? Mariah just said so. It must be true. So this is our problem. Remember, moles divided by molarity will give me liters. Do we have the molarity?
Yes.
Do we have moles?
We can figure it out from the grams.
but we can figure it out. We have 7.81 grams of NaCl. Guys, how do I go from there to moles?
Molecular weight.
1 mole over the molecular
One
weight.
mole over the molecular weight.
Okay. We also have what information, guys? Last problem right here. What other piece of information did we have?
Molarity.
So how am I going to get the liters?
Moles over molarity.
Okay.
Why is it not 5.532? Is there 2 sig figs somewhere?
Right here.
Oh, okay. I thought we were looking at the grams. Okay.
No. All right, one more thing. One more problem, and we are going to quit for the day. I realize we're very close to I got to get this in the slideshow. Thank you. Okay. Now, we have a certain amount of stuff dissolved in a certain volume, right? I add more water to this. Did I change how much of the solute I had in there?
No.
I've still got the same number of moles in there that I did before. I just changed the volume. If I have more water, have I added or taken away any moles of my solute?
No.
Add more? Add more? Have I added any more solute in there?
No.
No.
So isn't my moles of solute constant?
Yes.
Yes.
Okay. So I have my moles initial are equal to my moles final. How do we get moles? We multiply our volume by our concentration. So if I have my very, very first one that was down here, that had a concentration in it and it had a volume. So if I multiply my concentration by my volume, I get my initial moles of my solution. I haven't added or taken any solute away, so my moles of solute are going to be the same. But now I have a much bigger volume of that solution. And I still have my basic tenet. My moles, my volume of my final solution times my final concentration is going to be my moles final. The moles are not changing. My moles are not changing. So my initial concentration times my initial volume is equal to my moles, which is equal to my final concentration times my final volume. Now, as I increase the volume, what happens to the concentration? As I'm putting more and more water in there, what's happening to the concentration? Is it going
Becomes
up or is it going down?
going down, becomes more
Going-
dilute.
It's more dilute. So what you have to understand, if my concentration goes up, my volume goes down. If my concentration goes down, my volume goes up. We're going to start here on Thursday with our dilution problems, where we get our first concentration times our first volume is equal to our second concentration times our second volume. As long as you do not add more solute in there, this will maintain. Okay, guys. Are we okay?
All right.
Are
Yeah,
we,
I feel like I got a lot out of this lesson today.
are we okay, guys?
Professor, just one, can you please repeat what you said about the relationship between concentration and volume again?
Okay, Rosina, let's do some math here, okay? All right, say, I can't.
More concentrated than volume, I guess.
Let's do some math here, all right?
I got myself into trouble.
So did I. I just couldn't get myself out of it there. All right,
Wouldn't it be like making juice?
exactly.
Yeah, got it.
Say you have 2 molar solution and you have 300 milliliters.
Yeah.
What happens when you dilute that to 600 milliliters?
The moles will remain the same, but
Moles are remaining the same.
concentration is lower
Why is it lower?
because you have less solute for the amount of volume. Or
Exactly.
the other way around.
Exactly. So to do this math out, if I was going to do this, my solution would be 1 molar. Okay, Rosina?
Mm-hmm.
Just
Yes.
to give you an idea math-wise what's happening here.
Yeah.
Again, my volume went up, my volume goes up, my concentration has to go down.
Got it.
If my
Okay.
volume goes down, then my concentration has to go up.
Got it.
And the beauty behind this, it does not matter what your label of your volume is. It doesn't matter. As long as it stays the same, left and right on here, you don't have to do any conversions. Because if this were quarts and this were quarts, I would have to convert this from quarts to liters, right?
Right.
I would have to do the same conversion going from quarts to liters on this part. So the math would cancel out. As long as the label for the volume remains the same, you don't have to convert to liters.
Got it. Thank you so much.
Anything else, ladies and gentlemen? I'm happier with this than I was on Friday. I literally came out of Friday's lesson swearing at myself.
That sounds like you need
I
to
was
get
not happy. I was really not. Those of you that were in my Thursday lab understand that.
Poor
Okay,
guy, you hear all of that. You poor
Spencer,
guy.
you doing okay with this?
Yeah, I'm doing all right.
Okay. Let's see who's here. Let's see who's here and who's not. Gate. Gate, are you still here? Jennifer.
Gaith, we need a visual, man.
Yeah, yes, I'm here.
Kaylin, I saw her a second ago.
Yep.
Leandre.
Here.
Thank you. Lewis.
Here.
Fabiana.
Here.
Hey, sorry, Professor, I was in the bathroom.
All right, Kate. Mila. I saw
Here.
you.
Yeah.
Marie.
I'm here.
I know Mariah was here. Omar. Rosina, I know was here. Shamira.
Here.
Okay. Spencer, I just saw. Zaina.
Here.
Anybody who I didn't call?
Me.
Who's
Me.
me? Sorry, Armethea.
I don't think you called me, Professor.
Chase, I got you. Don't worry.
What about me?
I don't think you called me either.
Did you call me?
Cash, I got you.
Used to call me on your cell phone.
Okay.
Hunter, I got you. Who else? Who's the other female voice just heard?
Oh, that was
Aya.
I'm sorry, who?
Aya.
Aya, yeah, I got you, Aya. I asked you a question during the thing.
Oh, okay.
Anything else? Anybody else, guys?
You got my name right, Faith.
Yes, Faith.
all right, Professor. Thank you.
See you in
Those
lab.
Guys, those of you that are meeting in a half an hour for lab, I'm going to conduct this like a workshop, guys.
Cool beans.
Okay.
All
Have a
right.
nice evening. See you Thursday.
See you Thursday.
Have a good night.
Bye.
Bye.
Professor, do you mark me present? I don't know if you heard me.
Fabiana,
Yeah,
I got you.
So what do you mean, like?
thank you.
workshop?
Kate,
Yes.
you're asking a question.
Yeah, you were saying a workshop. What is it? What do you mean by that for the lab?
It's not going to be like I'm going to be lecturing you. Kate, you've really had all this stuff. I've been lecturing for the past week and a half on stoichiometry, right?
Right.
So, I mean, how much more are you going to gain from actually my sitting there and talking?
Probably a lot.
Or
No, I've
how
been
much-
watching like Khan economy videos on it too a little bit.
Guys, everything you can look at is going to help you.
Wait, so I'm just trying to get a visual here. So we're not going to be like, it's not a class. It's just like if you have questions, we ask you.
Gate, if you
He's
don't
saying
let me,
pretty much if you don't, if
Gate, you had the chance to go to the bathroom. I haven't. I just had prostate surgery.
Lord, go to the bathroom.
If you want a visual, I'll give you a visual.
Oh, okay. I'm good. Thank you.
All right. I will see you guys later in about a half an hour. Okay.
Okay.
all
sounds
right,
good.
I'll see you in the shop. Bye.
All right,
Take care.